The broadcast is now starting. All attendees are in listen-only mode.
Hello, hi, and welcome to the second session of the SimScale workshop on thermal simulations. I'm Ahmed Hussain, and today we will be talking about the conduction thermal analysis of LED considering three types of heat sinks. Before we start, I would like everyone to show me while showing the raise hand. You can click the raise hand button if you can listen me. Okay, I can see some. There are still some missing. Okay, perfect. Perfect. There are still one, two, three missing, I think. You can click again. I will say again. You can click the raise hand button to show me that you can listen me. And in case you cannot listen me, we have already emailed to you the toll-free number where you can call, and then you would be able to listen to also this. Okay, I think so far so good. It looks fine. So we would proceed with our workshop session. Okay, so today we will be discussing the basic phenomenon. So the conduction. So in the last session, um, my colleague Sam has already told you that how these phenomena works in simulation and also how important are they, so conduction, convection, and radiation. So in this workshop we will be discussing the phenomena of the conduction and how it can be used for some industrial cases. So for us now, the industrial cases we will be discussing here would be the thermal analysis of LED, which is really important in the electronic industry, considering three types of heat sink. That will be the consideration how we can change the heat sink and how the thermal conductivity changes, or the cooling of the LED changes. So little about myself before we go into the presentation. My name is Ahmed Hussain. I am an application engineer here at SimScale. I have done an MSc Computational Engineering here from Germany. My academic and professional expertise includes the linear and nonlinear finite element analysis, material modeling, and I am responsible here for customer onboarding and support mainly. Okay, so yeah. So next we go to the agenda. The agenda for today's session will be that the first point I would be actually talking about SimScale, what is SimScale, and what is the SimScale vision, and how SimScale is an online browser platform for the simulation and what it is all about. Then I will proceed with the importance of the thermal simulation in industries. Here I will be talking about actually how the thermal simulations can be used and normally are used in the industry, specifically in the electronics industry, and also in some of the other cases. Then we will be proceeding to the case studies where I will discuss that there will be like in this session today there will be two main case studies which we will be looking forward to. Then the fourth one would be how we can simulate these cases from SimScale platform. The next would be the live demonstration, so where I will show you the live demonstration of the projects which we have created on the case studies. Next up, we will be talking about the results of these case studies, and at the last, we will be taking question and answers from you. Okay, so first about SimScale. So the first cloud-based simulation platform in your browser. So all about SimScale would be in this section. So the thing is that normally is like you have a design phase where you actually design some product, and from going to the design phase, from design phase to the manufacture phase, you have a transition in between where you actually describe the physical prototype of your design. You test it for different aspects, for different trends, and then you go to the design changes where after the test you come to know, okay, there is some problem with your design and the physical prototype, then you have to make design changes, then you go back again, design it again, go to again the physical prototype, test it again according to some parameters, and do this again process over and over before you put it into the manufacturing phase. So this portion, which actually here shown here, is actually really costly and time consuming. This is the design cycle, which is really costly in case if you are actually producing, testing your prototype before putting into the manufacturing phase, testing it again, making a new prototype again, all over again before the manufacturing phase. So here where the simulations comes in. So what SimScale can do, for example, here is that this physical prototype to design change, this process can be actually done only into simple steps. So one is that you do the simulation of this your physical prototype before you put it into the manufacturing phase, and then over that what is done in the simulation, which is quite fast compared to if you do it manually every stuff, then you can proceed to the design change. Okay, and this process is actually really easy and fast, and it can be doable many times without producing some prototype or some without manufacturing some model. So this is all in the software side. So once this is done, then you can of course make the changes to design, do another simulation, make the changes, another design, and then do another simulation where then you can lead to the manufacture phase at the end. And this you can see that the gap which is actually here, actually it really reduces the amount of, for example, for this main phase where you actually decide the model. So this is the design process with simulation. So what you can get out of simulation, and here where SimScale actually really shines, because the cost to production ratio is really less. So the cost to testing ratio is really less. Okay. So one question would be that why we should simulate with SimScale? Why not with others? So this is where SimScale also shines. So what SimScale offers is three main things: is accessible, cost efficient, and for everyone. So accessibility is that for what you're getting actually is the hardware, which normally is not available to you easily, in your home computer or in your workplace. We give you a lot of computation power, so you are also having not only the so you don't have to care about also the software installation, but you also don't have to care about the hardware itself. So you can have high computation power, which is all in the cloud, so you don't have to care about that. So these two things are covered in accessible, so which actually SimScale offers. Then it is cost efficient, so it's free for public use, so you can make the free community account, and where you can actually test it. And other than that, a free professional account can be also made, where the professional features can be tested. And even if you buy, it's actually really economical, since the only way is that you actually spend on the core hours. So you buy the core hours, and then it's scalable and on demand. So if you demand more core hours, you ask for it, and we give you more core hours. So it's really scalable and on demand. And the third thing is it's for everyone. So as you know that we have now community, so there are many simulation projects in our community. One can share it with someone. So sharing the project templates and sharing other things is an really easy and um, one of the best feature of SimScale. Okay, so next up, I would discuss basically the types which SimScale offers. So first we will go through the fluid flow simulation on SimScale. So from the fluid analysis type, you can actually do incompressible, compressible, steady state transient, single and multi-phase flow, laminar and turbulent, scalar species transport. The one which are highlighted here in the bold are the one which are interested for example, this workshop, because these are the one which actually involves the heat transfer. So one is convective heat transfer, which is buoyancy driven flow. And the second one, which is a bit complex than this, the heat transfer, which actually, so the heat which is coming from from the fluid and going to the solid, and how the solid is heating, for example, is done by a conjugate heat transfer. In other words, called CHT. Then in the advanced applications, we can do you can do rotating machinery, EMI, MRF. Okay. So is it okay now? So I have this question here that mic voice is really low. So is it okay now? Can you please tell me about it? Yeah. Okay. Perfect. Perfect. Okay. Thanks for informing me this. I didn't know about here actually how the voice is working. Perfect. Now I think it's perfectly fine now. Okay. So in advanced application, you have you can do rotating machinery via AMI and MRF. You can also simulate the porous media. You can also do the sixth off motion, so 6 degrees of freedom, and you can also perform a particle flow. The solver codes which we are using are the open source from OpenFOAM, which is one is OpenFOAM, and the second is SU2 in this case of the fluid flow simulations. Then we go through the structure mechanics types which are available on simulation on our platform. So on SimScale, you can do static and dynamic analysis, both linear and non-linearities with different type of non-linearities, either material or geometric or physical contact non-linearities. You can also do the three types of vibration analysis: frequency, modal, and harmonic. You can also do kind of buckling analysis by using nonlinear elastoplastic material. And the third one is, which is important, for example, for this workshop, is thermomechanics, which covers heat transfer, simple heat transfer, where one can actually study the heat transfer, and uncoupled thermomechanical analysis, where one actually studies that how, for example, the stresses are produced because of the thermal load. Okay. Then the things which we support are the parts and assemblies. So you can simulate all of the big assemblies. You can define the context between them, all the physical contacts, or maybe the bonded contact between them. Different element technologies are available. Different material models are available with us. So for example, the hyperelastic material and also the plastic material. Then the solver interfaces in the background is the basic solver, which we use is Calculix. The advanced one is Codester, which really offers a lot in different analysis type, for example, static and dynamic analysis, and also thermomechanical and thermal analysis. So these are the two solvers which we are using in the background. Okay. Next up is the other simulation capabilities which SimScale also offers other than structural and fluid analysis. So one is uh, discrete particles. So you can also do the particle analysis. For example, you can see here how this simulation of the particles are being done. So it's bit different than what you have seen in the fluid. Fluid is that you have a fluid flow in which there are particles. So here you can see that these are only the particles. So the whole solid particles you can simulate. And other than that, you can also do acoustics. Somehow the frequencies of in acoustics actually, which you can see here in the car cabin on the right side. So in this case, you also have in the simulation capabilities rotating domains, multiple domains, different decomposition methods, and the solvers which are using which we use, for example, for the discrete particle is YADE, and there are also some commercial 3D parts, partially some third-party codes which we also use for different analysis types also. Okay, so this was for the SimScale, the introduction to the SimScale, what is SimScale and what it offers to our users. Then we will actually directly jump to the importance of thermal simulation in the industries, because since this workshop is about that how the thermal simulations, what is the impact of the thermal simulation in the industry, why industries use the thermal simulation. So the interesting thing here for us is the importance of thermal simulation in electronics industries, because today in this workshop our main focus is one of the case study which is of LED. So we will be discussing here that how the thermal simulation helps, for example, in the electronic industry. So in the electronic industry, the thermal simulation has been introduced in the recent years to really identify thermal issues during the design process phase. So the critical phase in the in the electronic industries, the design phase the industry, the company actually decide, okay, that you have a product, for example, a PCB, so printed circuit board, and on which the different components are being mounted. So the distribution, so how the components are mounted also makes a lot of difference. And the heat sink which you are using, for example, to take out the heat from those components are also of really interest. So what type of heat sink you should use, how the components should be placed, so you can avoid as much heat as so you can avoid overheating of your components, so you can take out as much heat as possible. So for that, so since the requirement of this is increasing, so the shorter design phase and the development cycle, shorter development cycle is increasing. The thermal simulations are really becoming handy in this case. So these thermal simulation can be used, for example, for the multiple stage of the design phase. So in order to identify these problems in the design phase before prior you go to the manufacture phase. So you can actually identify, for example, from thermal simulations these problems, and you can then rectify the mistakes. So it is really fast to do that, as we have discussed before also, that how the bigger cycle of changing the design and modifying a design, actually how long it is, and how simulation can make it smaller. So for example, on the right, this is taken from one of the website. This design cycle here you can see on the right. So this is the typical thermal simulation process design cycle in the engineering. So you have a simulation of the design concept. So you have a concept of the design that you want to make. You then proceed to the simulation of the preliminary design. So you decide one of the preliminary design, and you then simulate it for the first time, just to see that if it is working and how it is working. Then after that, you make several changes where you become satisfied at the end. Okay, now this is the threshold, for example, of the maximum heating of your component, and now your model looks good. Then you go to the final design. You manufacture, you actually not manufacture, you make a model of a final design, a CAD model, for example, and then you can simulate the final design. You simulate the final design, and then you rectify some minor changes in the final design. And after you have done over it, you can create a prototype which you can test, for example, also in your experiments, in the real world sense. And then you can go for the verification of it, according to some parameters, according to some thresholds, before you put into the production phase. So you can see that the three main process here are the one which are actually related to simulation, and how the simulation works here, how the simulation helps industries to solve their problems so easily and so efficiently. The next step is that how the steps are being followed in the thermal simulation in the case of, for example, electronic industries, to identify the problem sooner. So in this case, there are actually four main steps which are done. So one is that, first is that you make a concept simulation. So rather than making a full model, for example, so if you have a PCB, rather than of making a full detailed model of it, putting every resistor over it and the detailed resistance resistors over a detailed shape of the resistor, you actually make a preliminary or a concept model where you actually define all the, for example, ICs and everything with the small boxes. It's just a simple model to test it. You test it for some specific values, for example, for specific volume heat flux, for temperature change or something, for specific convection. And the main focus normally here is that you first check it, for example, first with the natural convection. So you don't allow the forced convection, for example, with a fan or something. So if you're testing a PCB, and you are not allowing it to cool down with help of a fan or some forced convection. So you do go with a natural convection to test it first, how the natural convection can help to take out the heat from it, so how much it is possible. So then you have some specific threshold, according to which you test it, that okay, now this concept model is actually good for some specific values, and it is good to go. And then after that, you come to the preliminary design simulation, where you actually do some preliminary design simulations on different design concepts. From that point of view, you can actually do different models, perform simulation on different models and decide, okay, which model is the best. Then once decided, you go to the final simulation design, and then you go to the verification of it. On the right side is a good data flow which shows how the thermal simulations helps you in thermal industries, for example, electronic industry here. So for example, you have a specification. In the specification, you actually design size, weight, and materials. And this you go give it to mechanical engineer, and mechanical engineer decide, okay, how the size, weight, and material, so which are the basic properties of the in the basic input to the simulation. This thing is provided to the thermal simulation software. On the other side, the environment conditions are also given, for example, the natural convection and forced convection. And on the other side, there are electronic engineers who are working on the PCB design. So how for example, for how the components are being placed on the PCB and how it should look like. So these all three inputs actually go to the thermal simulation software. You do the thermal simulation, and then after doing the thermal simulation, you can tell, for example, the mechanical CAD designer that, okay, there are some suggested changes to the mechanical design. Please make these changes and provide us back with it. The same way, you can also tell to, for example, electronics engineer that suggested changes to the electronic design are these. For example, PCB component layout should look like somehow different, so that we can have better results, and they do the changes. So these changes are done over and over, for example, for the design, and only the thermal simulation software is the one which is actually making the difference here. So telling the engineers that, okay, what needs to be changed. So nothing needs to be manufactured at this phase, just the simulations. And once this is done, then it's finalized. Then from all the mechanical and electronic engineering perspective, when it's finalized, it goes to the production phase. So when the product is actually, so this is how it is done, and it really saves a lot of time and engineering effort here. Okay, so next we will go to the importance of thermal simulation in other industries rather than the electronic industry, for example. So on the right, you can see that there are some applications which are already done with SimScale. You can, of course, find it in our public project page. The first one is the thermal analysis of heat exchanger using CHT. So to analyze the heat transfer between a whole hot and cold liquid domain. So here we are analyzing, for example, that there is a cold liquid running in, then heated water comes in from here, and actually it heats up the going inner going off the heats up the inner cool water actually here. This type of application is really common. For example, the working of the radiator of a car is also the same thing. So you have a cold water inside the radiator, which actually runs through all of the engine, and it actually cools down the engine. So this is one of the example of how the heat exchanger works. The second one is here on the right. You can see on the right top is the thermal analysis of the light bulb using convective heat transfer in CFD in order to analyze the heating of the filament. So in this, you can analyze, for example, that how much the filament is being heated. So is it not? Is it safe, or is it overheating? So one can actually do the convective heat transfer simulation here to see that if the filament is okay or it's overheating or not. The third one, for example, here is the room cooling, the server room cooling. So there are different servers being placed in the room, and there is the simulation shows how the cooling of the server actually takes place. So it's really important. For example, in the case if you have a big server rooms, normally they get really overheated in the room, and the overheating of the room can be actually neutralized with the effect of cooling, and then placing of the cooling systems are really important here. So this is how you can do it with simulation softwares. And then last one is the thermostructure analysis of steam stop valve here on the right side. So it's one of the steam stop valves. So it's used for stopping the highly heated, for example, steam. So for that, the thermostructure analysis is being performed, for example, here to see that how the effect of the heating or the thermal effect of the steam affects the overall valve. So the stresses, you can see that how the stresses looks like, for example, on some specific edges of the steam valve. Okay, Now, once we are done with here, so we will go to the case studies here. So we have actually decided to give, like, for example, two of the main case studies here. So one would be with the only the heat transfer thermal solver, and one would be the thermomechanical solver. So the first case study, which is really important now, is the thermal analysis of a LED, so light emitting diode, considering different heat sinks. So you can see on the right, there are three types of heat sinks which has been used, for example, for this case. So there is an LED which is mounted over here, and there are three types of different heat sinks which is being used. So one is the plate fin, which you can see here, though it's like flat plates. The second one is inline pin fin, so they are like pins, so they are like the form of the plate, which are also cut it from inside here, and they are like pins, and now they are inline actually, so they are just in front of each other. The third one is the same thing here, but it's actually staggered, so every pin is actually not in front of the other, so it's like in the zigzag fashion. So these are the third cases which we will study. And the aim of this is to study the conduction between different components and different materials here. And the other thing which is really important is to see which heat sink type is best for the LED cooling in this case. The second case which we will be discussing will be the thermostructure analysis of a spark plug. You know that spark plug is really used in the automotive to in the combustion engine of the cars, where it actually is used to ignite the fuel. So uh, since the ignition is happening, and ignition happened with a really high temperature, and you can feel that how high temperature actually touches the lower ends of the spark plug. And so the study of the spark plugs here is really important to see, okay, how the thermal effects are being formed inside the spark plug, and how these thermal effects are now affecting the stresses inside the spark plug, and how the spark plug is being deformed, or spark plug is being stressed out because of these thermal loads. So in this case, we will be discussing actually two types of design in the spark plugs. On the left, you can see one of the design which is taken from the GrabCAD provided by one of the user, which has a little bit. You can see a thick insulator here. On the right side, you can see a design with a fairly thin insulator here. So the insulator here is a bit thin, and of course the design here is a bit changed here. So right here you cannot see the connection, for example, of the insulator with the outer shell. And aim of this study is that to study the heat conduction in the spark plug, how the heat conduction is taking place, for example, in this case. And the other very important thing is that how the stresses are being formed because of this high thermal load, which is being provided from on the lower faces of the spark plug here. Okay. So for the simulation details which we will be discussing here is I will be going through it really quickly for the analysis overview, what type of analysis is being used for these type of case studies. So for example, for the case study 1, thermal analysis of LED considering different heat sinks, the analysis type which is used is steady state heat transfer. So it's just simple steady state, no transient effect. So only we are interested, for example, in the final state. So that's why we do we do a steady state heat transfer. And in the boundary condition, we would actually apply a surface heat flux where LED is actually mounted over that surface. And the other thing is the convective heat flux over the, for example, faces of the heat sink, considering that the air is touching the heat sink and how the convection is going on there. The total simulation time would be around 1 second. So it's like 1 second, one step simulation with the steady state heat transfer. The simulation output which we will be interested in here is the heat flux and the temperature distribution in the domain. For example, in this LED whole domain, the heat sink and different components in between, and then the study of heat conduction in different materials which are placed over each other in this case. The second case study would be the thermomechanical analysis of a spark plug, which will be also steady state, since we are also interested in the final state of it. But in this case, it would be steady state uncoupled thermomechanical analysis. So this would also include the heating of the general heating of the spark plug, but also the stresses being produced, or because of this thermal load, the stresses and the strains being produced inside the spark plug would be also taken into account in this case. And the boundary condition which will be used is the cyclic symmetry. I will come to it in a while when I will be showing you the analysis in the browser, in the platform actually. So cyclic symmetry will be used, the fixation would be used, the one would be the temperature would be used, which would be applied, for example, in the on the lower side of the spark plug, and then convective heat flux also will be used, for example, the touching of the ear on the outer side of the spark plug. In this case also the total simulation time is just 1 second. It's only one step simulation, the steady state, and yeah. So the other than the what we have discussed at the simulation output and the previously, the other one would be the study of the thermal stresses inside a spark plug which are being formed because of the thermal load, which are also really interesting in this case. Okay, now yeah, next point will be to show you how you can actually simulate with SimScale platform. It's really three really easy steps, which is one of like pre-processing, you have then the analysis phase, and then you have post-processing phase. So in the pre-processing, you have a CAD upload. So you upload a CAD model. Simply, for example, you can see that it's the first model of the heatsink study of the LED. So the plate fin heatsink. So here we have uploaded, for example, the model. Then next step is to create a mesh. So a reasonable mesh where you can actually perform the simulation on it. And then you actually use this mesh, so this domain, to simulate. So you set up the simulation, for example, in this case, steady state heat transfer, and you do the simulation over it. Then after a while, once your simulation is done, you get the results. So you can post-process the results then in the post-processor. So these are the three simple steps which you can do under one workspace on SimScale platform actually. So after that, I will like to switch to the live presentation on SimScale platform. So yeah, so now I switch back to the platform here. So you can see that this is the first simulation case study. So first case study where we will be discussing how change, how changing the different heat sink for LED actually helps us. So for example, here you can see that this is the first model. The second model is the LED with inline heat pin fin. So you can see that how it looks like different. And this one is the staggered one. Okay, so we have a okay, so we have question here. So there's one question. Okay, so the question is that what is the difference between what is the meaning of functionality and environment condition in the flow chart of the model? So okay, so if we go to the flow chart of model here, the environmental condition, as I have referred to, is the conditions from the environment. For example, in this case, for example, the example of the LED, for example, in this case LED, the environment would be that how the heat sink surfaces are touching the air, so the outside air. So is the outside air static? So is it like a natural convection, or you have actually a fan, which is taking out the heat, or if the air is flowing over the heat sink. These are the conditions which are the environmental condition which actually affects a lot. So if you have a blowing fan, for example, the convection would be more. So in that case, the heat loss would be more. So these type of, for example, environment conditions would be also given to the thermal simulation software, where you actually then can decide, okay, is the natural convection is okay, or we need a forced convection or not, for example. So these are the things which are considered in environmental conditions. Okay, so we come back to the live presentation. Okay, so the third type, I hope I answered your question. So if you're not, then of course you can ask again. Okay, perfect. Okay, so this is the third model. So it's the staggered heat sink. So the difference between the second one and the third one is that they are not aligned, for example, in this case. So they are just staggered. So they are in the zigzag fashion, for example. Then I will show you quickly the mesh. For example, here the mesh is made with some refinements, for example. So refinements are used to get nearly similar or get a good mesh, for example, on different solids than the other one. For example, in this case, you can see that how, so if you create automatic mesh, it can be possible that you are only having one single element here. So with the help of, for example, or, the tetrahedral with local refinements, I plan to give the refinement, for example, to this solid. So so two elements would be sitting here. So for example, to have a good results in the thermal simulation. So this is the, for example, the mesh for one of the case, for the one of the first case. Then we will proceed to the simulation designer. So the setup of the simulation is all the same for all of them. So nothing is changed. So only the model, the new domain is given to the next simulation, and it is being set up with the same settings. So if I go through the one settings, it would be the same for the other also. So we will go actually to the one only. So first, you can see that here the heat transfer is being selected with a steady state. So we are using steady state because, as I told, that we are interested in the final setup or final step of the simulation. So steady state would be good for us. Then the domain is being selected, which is the first one. For example, here I can just quickly switch to surfaces, so I can actually handle it quickly. Okay, so the first thing is that contact. So you can see that there are many solids here, so which are actually different layers of different materials. So in LED, there are different materials beneath it, which actually should be taken into account. And before that, the heat sink cannot be mounted directly. There are some materials which should be here, which is these materials are actually taken from the one of the paper, which is also mentioned in the project description. So one of the paper through which the material properties were taken into account, and the thickness, and all the things of the dimensions of it also. So here you can see there's heat sink and different materials here. So first thing is to define the contact between them. So if you don't define the contact, for example, between them, there will be no heat transfer taking place, which we don't need. So we need to define the contact. So for example, here is a die and die contact. So there's the die and die attach contact. So you can see that this is the die actually, and this is the die attach, which attach this die to some of the other material, and this is the contact between this die and die attach. Similarly, you have a die attach and copper contact. So you're here, you define the master one as surface as the master, second as the slave, and the contacts are being defined between them. And then the copper dielectric layer, and aluminum, similarly aluminum and tin contact. So tin is here, so it's a thermal insulator material here, so which is connected to this aluminum thick plate. And then TIM and heat sink contact here, so thermal insulator and heat sink contact. So these are the contacts which are being defined here. Next up, we define the materials. So we have here silicon, disilicon, which is made of silicon. So this is where the LED is being mounted. So here you cannot actually see the LED. So we just omit the LED because we are not, for example, interested here to see the thermal, for example, the heating of the LED itself, but we are interested that how the heat is being transferred from the LED to this silicon die, and after that how the heat is being dissipated from whole of the system, and how the conduction takes place inside. So this is the die which is made of silicon. So the properties are given here. This is the die attached beneath it. Then you have a copper plate. Then you have a dielectric layer. Next up is the aluminium plate here, a thick plate. Then you have a thermal interface material, so thermal insulation type material here, which has really a low conductivity. And then you have a heat sink, which is also made of aluminium here. So these are the material properties which are given, for example, to this whole model. Then for the initial condition, initial temperature of 297 Kelvin is being defined here. Yeah. Next up is the adiabatic boundary condition. So this is actually just defined here. So on the surfaces which are actually symmetric, for example, this whole model is actually the full model. So it's like it should be like the full model, but since it's symmetric, we have already only taken by the 1/4 of the model, so not the full one, to save the times, to make the mesh size really smaller. And the adiabatic boundary condition is being given here. So this means that there will be no heat transfer would take place here. So even you can avoid it. So you don't have to even give it. If you don't give any condition, for example, on these surfaces, it would be fine. So it would be just taken as the same as we have given here. This is just for understanding. You can, of course, avoid it also. Just omit it. So it's not a problem. Then you have a uniform convection heat flux, which is applied on the surfaces of the heat sink. So this we consider that there is some air which is having a value, so a convection of 10. That means that there is a air which is kind of static, but yeah, with a convection coefficient of 10. with the same heat transfer value, so the same value of the room temperature here. So these surfaces are being exposed to air actually in this case. Then you have a uniform heat flux which is applied on over this LED. This is according to some watt. So you have the area of the LED. So the whole area of the for the full model, you divide it with the watt which you have taken for the LED, which is in this case 1 watt. So it's a 1 watt LED and it's being applied on this surface. So this is the value which is actually coming from there. So the heat flux will be applied from here. That means the heat coming from the LED. So heat dissipation from the LED of 1 watt in this case. Then nothing is changed here. The single step simulation, because it's steady state, the cores are changed to 16 since the mesh was a bit bigger, and the output was taken as a temperature and heat flux only. And you can see the simulation takes only 5 minutes to complete, and you can just post-process the results. So I have already opened the results here, but we will come back to the results later on. So before that, we will go to the second simulation case. So the second case. So for the second case, we are discussing here the thermal structure analysis of a spark plug. So this is the model of the spark plug, which is also taken from the GrabCAD. So one of the user has provided this model to us, and we are interested in to simulate this. So you can see that this model is quite detailed. You can see, of course, these spirals here for tightening of the spark plug, and there are also many the embossed marks of the company name and the model name is being embossed over here. So this is basically now the model where the cleaning needs to be required. So you really need to clean before you create a mesh. So these small faces where the information is being imprinted over it, so one can avoid it. The next thing that one can avoid is the spirals. For example, we are not interested in the spirals. These can become complicated in the meshing or something, so we can just make it flat. So just to make it simple. So you can see this. The second thing is the simplified model. The first simplification is that the removal of these all all the monograms or all the embossed marks here. And then the second simplification is the removal of the spirals to make it just flat, to really make it simplify. And by doing this, then you can see now the model has now become symmetric. So you can, rather than taking the full model, you can take only the 1/4 of the models, which is actually shown here. So this model is now taken here as a small one. So you can see that you can take only the 1/3 of this model to simulate it. So like a 60 degree of model somehow, or 120, yeah, 120 degree of the model somehow. Okay, this is the first model. So the second model which we will be discussing is this one. So you can see that there are some changes. Now the insulator is a bit thin, and it is also not connected, for example, here. So this is a minor change which is done to the model. There's more surface area where the heat would be applied as compared to the previous case. For the mesh case, you can see that here I have, for example, created an automatic mesh. So with the automatic mesh being on moderate, you can see that, for example, that the interface where the contact should happen actually, they are not having the consistent mesh. So the mesh consistency is not there. So this is really a problem in the case of, for example, thermostructure analysis. Then you would probably see not a proper distribution of thermal load, and also the temperature would not be properly distributed between these interfaces, and so it will lead to some unusual distribution of the stresses. So you have to make sure that in this case make the faces having the same type of mesh, mesh density over them, for example, which is created here. So this is done with a tetrahedral with local refinement, and as you can see here that this mesh is similarly of the same size which was before, but it also has this refinement which is given on all the faces. The same refinement is given. For example, you can see now how the consistency of the mesh looks like. And yeah, this mesh would be good to go actually for us, and the same mesh technique would be used for the second case also. Next up, we will actually lead to our simulation setup. We here selected an uncoupled thermomechanical analysis, advanced in this case. Advanced actually allows us to have more boundary condition. For example, cyclic symmetry, which we want to use here, is not available in simple uncoupled thermomechanical analysis. So we have selected here the advanced one. The analysis type which is selected here, the steady state, as I told already that we are interested in also the final state here, and the loading. So this is the load type or the analysis type of the mechanical here, so which is static or dynamic. So our case is static, and we haven't created the nonlinear analysis being, so it's being false. So we are not considering any nonlinear effects on, for example, the material nonlinear effects or something like that. Okay, then we have decided the domain. For example, in this case, the symmetric mesh for the first model, which you can see here. These are the simple contacts which are being defined between all of the materials here. For example, shell and insulator contact. So this is insulator here, and here is the shell, which is, so the contact between these two things are defined. Insulator with terminal contact is defined. So here insulator and the terminal contact, here is the terminal, and terminal insulator contact is defined. Insulator terminal electrode contact is defined. So here is in the blue, you can see the electrode, and the contact between electrode, thermal insulator, and the terminal is being defined here in this contact. The important one is this one, the cyclic symmetry, which I was talking about. So for example, in this case, you can see that we have taken 120 degree of the model, so not the full of that, so 1/30 you can say in this case. So the cyclic symmetry allows you to apply the symmetry along this model. So you can see, for example, here that our model is actually cut it here, for example, on this side along the x-axis. So I will make, for example, this master, and then I will make this as slave, these surfaces. So you can see that now these surfaces are slave, and now according to our right hand rule, you can say that, you can see that the right hand rule shows, now in this case shows that, okay, this is my vector in the y direction, so it's in your thumb. A thumb will show that how your vector looks like, along which the rotation will take place. So from the slave surface to the master surface to define the cyclic symmetry, and your curls of the fingers would show that how the slave surface are being, being projected on the master surface to restrict this model in the cyclic symmetry sense. So in the cyclic symmetry, so define the cyclic symmetry. So this angle is defining that how much it will be rotated. So 120 degrees the cutout. So this angle from here to here is actually 120 degrees. So this slave surface will be now projected according to this rule to this master surface. Okay, so this is how the cyclic symmetry is being defined here. Okay, so then the materials are defined. So here you can see that this is defined of carbon steel, the shell and the electrode itself inside, the terminal, sorry, and the electrode is being defined of nickel in this case, and the insulator is being made of ceramic here. Okay, so we have a question from Joseph. He said that at thermal contact, do you define a contact resistance value? If not, does the program assume perfect thermal contact? Yeah. So right now, the thermal resistance, the thermal contact resistance is so far not available on platform. So right now, it actually defines the perfect thermal contact for sure. So there will be thermal contact will be perfect. So to define, for example, the contact resistance, the one idea would be there to define a thin material between that, and define some conductivity value to it, some low conductivity value, and it will actually act as a thermal resistor. But right now there is not a possibility here to define the contact resistance value between. Okay, so I hope I answered your question. Okay, there is another question with from Ritpal. He says that what is the difference between edge adaptive mesh and mesh refinement manually? So the adaptive mesh, so the automatic mesher actually meshes according to the domain of the model. So it actually adapts the parameters of the mesh according to the size of your model, the whole geometry, for example, the whole assembly. With the mesh refinement manually, you can actually define a global refinement where the refinement will be applied to the whole model. But other than that, you can actually define some refinement zone, for example, some faces or some volumes, where you can actually define some refinement level where that refinement will be actually followed. So that is the difference. So you can actually define manually where you want to refine the mesh and where not. Okay, so Joseph said that lacking the ability of define thermal contact resistor, why define thermal contact pair anyway, since the program uses perfect thermal contact anyway? Yeah, that's right. So program uses perfect thermal contact anyway, but if you don't define the contact, there will be no distribution of the heat. So this contact actually defines the distribution of the heat between the materials, so between the different components. So if you don't define it, there will be no heating. So if, for example, in this case, if you're heating this insulator and it's not being in contact with the other other materials, there will be no heat transfer will take place. So there will be only the heating of the insulator which will take place. So you have to define the contacts to define the, okay. Okay, perfect. So yeah, so moving on, we have defined, for example, here the cyclic master. The cyclic master we have restricted in the x direction, so you can see that it is being cut it along the x-axis. So now the x restriction is defined, so it is not allowed to move in x-axis. So this will actually restrict the symmetry. It will not allow the symmetry to move in x direction. This is the only constraint which we would want to do here, which we have to do here. So that's it. Then the next thing is the fixation, which we have defined here. For example, here where we assume that, okay, now it's being screwed in to the place, and now it's being fixed here. So it's not allowed to move in any direction. So every direction is being fixed. Next up, we will go to the thermal load. So the constant temperature of nearly around um, something like 530 degrees, for example, is being applied here. So on the 803.15 Kelvin is being applied on the inner surfaces here. So these inner surfaces you can see which will be actually come into contact with the fuel which is being combusted, and the heat will be actually touching here. And then you have air convection, which is applied actually on the upper side. So this is actually closed because of the cap over where the electric the electric current is being passed here. So other than that, these are the surfaces which are normally exposed to the air, and here a value of 25 is being applied since the air will be flowing over the surface, and that's why this value is a bit higher. And the temperature is taken somewhere really high, which is inside the car. You normally can feel that, okay, there is a temperature, some constant, some temperature is there. Okay, there is another question from Joseph. He said, in the meshing phase, do you have to have a conformal mesh, meaning that you have to have node-to-node connectivity between nodes across different material blocks? Um, no, you don't have to. If you don't want, if you really have a consistency already so much, then you probably don't have to. But in the case of thermal analysis or thermostructure analysis, it's recommended, since if you don't have the conform mesh, then the distribution of the stresses of and the temperature would be odd, since the solver wouldn't be able to solve it perfectly fine, since node is not sitting over each other. And then you will see that there are some regions so some nodes have less temperature, some nodes will have more temperature, and because of that, the thermal load would be different, and that's why the stresses would be also different. So okay, so then the numerics, nothing is changed, and here you don't have to define anything that steady state, since it already automatically takes a single step, and then the simulation only takes 7 minutes. So first it do the thermal analysis on this part, and using that thermal analysis out as an input to the structure analysis, it takes out the stresses from this model. And the output which is taken here is temperature, displacement, Cauchy stress, uniformity stress, and total strain. Okay. Next up, we will actually come to the results. So now we will discuss quickly the results and how they look like. So let's go for the first case. So here, the first case, which is simulated on the LED being mounted on the different heat sinks, or you can see that the difference, that how the temperature is being distributed along all of the LEDs. So the temperature range is being arranged according to the first model. And you can see that as we are moving on the right side, so changing of the models, you can see that the sink with a pin fin, so a simple, aligned inline pin fin is a bit heated more than the normal plate one, but the staggered one looks the most heated one. So it clearly shows that how the model of the heat sink, if it's changed like that, how the distribution of heat would look like, and how much the LED would be heated. So you can see that here the LED looks like being very much heated compared to this model, and this is simply due to the reason that this heat sink actually has larger surface on which the convection is being applied. So there are larger surfaces of the convection, so air is touching on the larger area, therefore the heat is being taken out really quickly as compared to the other one. So this is the normal description of how they look different in this case. So and here also you can see that the staggered one actually has less number of pins as compared to the inline, and that's why it's more overheated in this case. So this analysis shows that which would be the good choice for the heat transfer, or for the LED, the heat sink for this case. The next up, we will discuss here the stresses, for example, in this case for the thermostructure analysis which we have done. Okay, so there's one more question from Joseph. He said, are these models available online for us to practice after this webinar? Yeah, sure. I will actually pass over you the link also at the end of the presentation, and I will also show you that where are these projects, and you can search, of course, and they are available online. Also in post-processing, can we change the units of display from say kelvins to, no. Right now we can change the units from Kelvin to Fahrenheit or for example degree Celsius. It's always Kelvin, but of course, if you have given everything in Celsius in your simulation according to Celsius, then your units will here show as Kelvin, but it will be actually Celsius. So that's how you can change your units to Celsius. But it's always recommended to do your simulation with Kelvin, since we SimScale uses SI units, and we actually prefer to have the Kelvin. Okay, so here in the post-processor, you can see that how the stresses looks like in both of the models. So the left side is the first model, the second one is the model with less insulator where the heat is being applied on the larger area. So if we go, for example, here, I can, for example, rescale my stresses to, for example, this value, and you can see clearly that how the stresses looks like in this case. For example, you have in this area nearly a high stress in this model case, and also in this area where this insulator is being attached. And now here are more stresses, and the stress distribution looks completely different on some areas of this spark plug. And on the back side, you can see that the second model is actually having more stresses on this area than this one. If we go even more, for example 1E9, so this area is more than having 1E9 stress. It is stress out, and you can see that how the first model actually has the stresses also in the electrode, and this is because of the reason that this connection which is done between insulator and this shell, this actually is producing stresses. So you have a thermal load that is actually pushing this insulator inside. That's why you can see the stresses here, which are normally minimal here. And because of this reason, you can see that electrode is having a little bit stresses here. And overall, if you see that there are actually yeah, so overall you can see that there are actually more stresses on the top here on this case, and also the electrode is here having stresses. So both models are considerably good, but I think the first one is good in the case that it is not allowing more stresses to go on the top as compared to this. So electrode doesn't have that much stress, which is having a quite low value, which is quite okay in this case also. The next up would be that we can actually load the temperature case, the thermal case. Okay, so Amritpal says, so the question from Amritpal, he says that many times I do not understand the reason of rescale. Could you explain fundamental behind of that? Yeah, of course. So the rescaling actually, if so through rescaling, you can actually rescale the values which you are interested in to see. So for example, that in case of, for example, in case of nonlinear materials, you have a plasticity. So you have a yield point, for example, and after yield point, your yielding will start. So for example, if you have a yield stress of 250 megapascal, that means that after 250 megapascal, if there is a stress in the model, that means it's plastically deformed. So you can actually, for example, rescale your scale here from 0 to, for example, 250 megapascal, and then you would be able to see the red region. So with the red region would show that, okay, for example, in this case, these are the areas which are being yielded. So these are the importance. So this is the importance. For example, if I rescale it back to normal, you can hardly see any difference between the stresses here. So by rescaling, you can actually see the difference. So there is one more question from Joseph. In the stress analysis module, is there a way to define paths to perform stress linearization type analysis? I explained the SME section, this part 5. Okay, I'm not sure about this SME section 8. Do diff to part 5, so I'm not sure about what you're talking about, sorry. So a way to define paths to perform stress linearization type analysis. I'm not sure about really, Joseph, what you're talking about here, because I really don't know about this ASME section 8, sorry. So probably it would be great that you can actually put this question later on in the forum post, which we have created also for this session. So you can put the question here, and yeah, I would come back to you afterwards there. Is it fine for you? Yeah, we have elastic plastic material model in structure analysis we have. If you switch it to nonlinear analysis, then you can find it. We have it. Okay, Joseph has this question that do we have elastic plastic material model? We have. Okay, so this is the importance of how the scaling works. Okay, since we are just reaching time, I would just fast over this thing. So this here. So for example, now we are looking at the temperature distribution. So over the spark plug. So you can see that how the temperature distribution looks like here. The little bit heating is going more as compared to this one, which is a bit cooled down in this case as compared to this one. And this is probably due to the reason that this thing is also connected here. So from the insulations there are some thermal so temperature change coming here from this type this, and that's why it's a bit more heated. On the other side, you can see that since this is having a larger area than this one as compared to this one which is have less area, you can see that the temperature is more here as compared to here. So you have actually a nearly orange area here which is nearly around 750 Kelvin compared to the 800 Kelvin all around here. So this is also one of the example that how this model is, for example, much better than this one in case when the high thermal load is being applied to this spark plug. So this is being less heated as compared to this one. So this is quite a nice model in this case. Okay, so coming back to the presentation, I will now look forward to, okay, go to one of the more other case, which is really interesting. So this graph, for example, this shows for the case study one, where we do the simple LED analysis with different heat sinks. You can see that how the temperature change along the different materials take place. So this is die attach, copper, then dielectric layer, aluminum, thermal interface material, and then comes the heat sink. So this is the first for the blue one. You can see that it's a plate fin heatsink, the first model. The second one is inline pin fin heatsink, and the third one is staggered pin heatsink. So this is how the model looks like. So how the distribution of the temperature looks like. So you can see that it nearly starts at 324, the case of staggered pin, whereas there is a difference of like approximately like 1.5 or 2 degrees here in case of plate fin. And how the distribution of the temperature looks like. Now at the end you can also see the same difference on the heat sink, that how much is the heat sink being heated. So it really shows that the model which is taken in the plate fin heat sink model is much better, for example in this case, to take out the heat from the LED um, as compared to the one. Okay, so there's a very low sound volume. Sorry for that. I'm really keeping it on my just near to my mouth, the mic. So probably I don't know why it is sometimes really low. I think it's okay now, right? Can you confirm? Is it okay? Okay, better. Okay, perfect. Okay, so this thing you can see here. So this model, how it looks like actually. So the here the graph clearly shows that which model is the best. So the plate fin heatsink, for example, it's in this case. Okay, the last thing is that the links to the project. So there are these two project links for the spark plug and the LED simulation, which you can find here. And I will actually quickly show you that where you can find it. For example, in this case, you can find here this one, which is thermal analysis of heatsink LED. You can just search it over like LED in public project library, in the public project page. You can just write LED, and then you can find here on my ID, which is Ahmed Hussain 18. For example, you can find this project. Okay, Joseph has a question. The plate fin design also shows that we may have too many plate fins. Some of the fins away from the LED may be removed. The plate fin design also shows that we may have too many plate fins. Yeah. Yeah, actually, it's according to one of the, as I showed, that it's according to one of the theses which is being followed. For example, in this case, of course, the model can be changed, but it was just followed because of that. The model change can actually, you can decrease that, and of course, you can actually take into account that decreasing these plates and then simulating it with that model, that how it actually takes place. So how the cooling of the system would take place. Okay, so this is here you can find all the information on this one, and the second one is you can find, for example, here. So for example, just quickly. Okay, I just close it. Probably I can just go to the dashboard here. Yeah, it's taking just usual. So yeah, but in meanwhile, I can show you that here there is a session to discussion for the conduction is being made already. So here you can discuss this this workshop here. So any question if you have, any suggestion if you have, you can just post it here. Okay, so this is the project thermostructure analysis of a spark plug, which you can also find in the page, in the public project page. Okay. Okay, so lastly, question and answer. If you have more, you can just ask now. So I will be glad to answer. Okay. So far no questions. I think we are good to go. Okay, perfect. Okay, thank you so much. Thank you for the joining, and I hope to see you again. For example, not me probably. I think Sam probably would be also taking the next webinar, so the next workshop. So yeah, I'm hopeful that I'm hopeful that you will enjoy also the third one, the third session, which is on convection. So more to the CFD side than to the structural side. So yeah, so see you then soon. Then have a nice time and enjoy simulating. Bye.